We're going to get started, and we'll jump back into the bus in a second. You guys remember the bus? Near and dear to everybody's heart. I want to get started, though, open it up and talk a little bit about the exam, if any of y'all have questions. I know I sent an email out about the exam more broadly, and I think just to touch on what it's going to be, right, the main thing that we've done and that we've thought about and looked at are like pipe flow type problems. And really the equation that a lot of the stuff that we've done in the last number of weeks, right, really boils down to understanding how to look at this equation. So alpha 1 b1 squared over 2 plus g z1 2 plus g. Make that look like more of a 2. Yeah. So really a lot of what we've done comes down to understanding how to use and apply this equation in different situations. Some of the early stuff that we did with Bernoulli's equation head loss is just 0. Because we don't have friction. We talked quite extensively about different ways that we can use to model head loss for laminar flow, for friction, for turbulent flow. What are ways we derive some models for laminar flow directly from the Navier-Stokes equations, but kind of boiled it down to this type of a model. So we saw a little bit where those came from. The Navier-Stokes equations, there's not going to be stuff like, hey, here's the Navier-Stokes equation, derive blah. That's not a great exam question. We've done quite a bit of that actually in homeworks and in class and different places like that. So that's not going to be on the exam. We might use the results of that, for example, like calculating head loss, and a lot of our models really come out of Navier-Stokes, but it's not. I'm going to give you this whole big equation and you have to simplify it and cross out terms and integrate and figure out velocity. Like, we're not doing that. Most of it will boil down to things like this. So I guess what I mean by that is think about like all of the stuff that you had to do and think about for your project. That's a big part of what we've done, and like building up to that and actually doing that over the last number of weeks. So things like figuring out losses in pipe problems and figuring out, you know, what size pump is required to do something, or what size turbine works for. So different things like that are going to be all things that are kind of fair game on the exam. Obviously, I'm not expecting you to like do anything as in depth as what you did for your project, but you know, you could maybe see a snippet here and there of something similar to that. I'm not going to pick parts of the project and put it on the exam. But you'll see, yeah, problems for kind of broadly using this model and understanding this model, and major losses and minor losses and how all of these things connect. So as far as things to study, homework, what was it, homework 8, that was extra credit. It's homework 8 or 9, I would have to look it up. The one that was entirely extra credit, that would be a good thing to look back at. The extra videos that we made around the design project, like for pumping and for fluid flow, those would be good things to take a look at again. And then there are also a lot of example problems in chapter 8 that would be good things to look at. So I would say, like, as you're dividing up your study time, probably spend more time looking at chapter 8 than anywhere else. Because a lot of the stuff that we did before that was, in like the recent past, was building up to the stuff that we ended up doing in chapter 8. Like Bernoulli, okay, Bernoulli is the exact same thing. It's just we did frictionless. So we said that the head loss was 0. So like you don't need to spend any extra time dealing with that. Is like if you understand this top thing, you understand the ideas behind Bernoulli's equation. The only difference is that it's frictionless. So spend most of your time in chapter 8, probably in chapter 8 type stuff. There's other things that could be there. So there could be something, right, what other Bernoulli equation stuff? So like Bernoulli equation thing, we talked about like a pitot tube and manometers and pressure measurement, dynamic pressure versus static pressure. So there are some other things kind of a little bit outside of chapter 8 that are also possibly going to be covered. But like I said, I expect the majority of it to be chapter 8 type stuff. If I were to put a percent on it, I don't know, maybe 80% of it will be chapter 8 or like related stuff, and the other stuff might be, you know, kind of scattered here and there, or part of a bigger problem that you have to look at. Any questions from the in-class crowd or the virtual crowd? First, Barry.
Is the key for homework 9 posted?
So is the key for homework 9 posted? Is homework 9 the extra credit one? That should be posted. If it's not, bug me about it. But I think I made that live the other day. So I believe all of the assignments except the last one should all have keys posted. Okay, are there any other questions? Okay, a question from online. How many questions do you anticipate it being? I'm not 100% sure, probably 4, but maybe 3, maybe 5. I have a couple questions written and I have to actually take it and time myself and figure out how long it's actually going to be. Probably 4. Ryan's begging for 3, then they're just worth more points. They're harder and worth more points. So I don't know if that's necessarily beneficial. Okay, so I'll be available if you have questions. Shoot me an email, and I can try to respond to that. But that's coming Monday, so spend a little bit of time as you're basking in the sunshine this afternoon, thinking a little bit about fluids as well. Like as the wind blows, you can think about boundary layers forming and pressure differences and right, lots of fun stuff. Okay. We were talking about last time, which was quite some time ago, all the way back on Monday. We were talking about this bus, and I was told that my bus model wasn't very good. So here's my new and improved model bus. It is a 1/16 scale double-decker London bus. A very good drawing, I might add. So the idea that we're talking about is it's a pretty cool one as far as experiments go. So the connection between a model system and a real full-scale system, and how do we actually make that connection functionally? How do we do an experiment at small scale and connect it to what's happening at large scale? Ideally, we have to do 3 things. We have to get the geometry to be the same. So if our scale model has to be an accurate representation of the full size thing. We have to have kinematics, so that's geometric similarity. We have to have kinematic similarity, which means that like the flow has to be the same. So for example, in our bus, if we're looking at it driving down the highway, like into the wind, we have to have our model in the same kinds of conditions where like the wind is blowing into the front. Okay, so those two things have to be the same. Then we have to match what we call dynamic similarity, which is matching the key dimensionless parameters. And if we can do all of those things, then we can directly translate our scale model experimental results up to our full-size model real system, which, if you think about it, is a super powerful thing. We can take measurements, any measurement we want. If you want to measure dynamic load, if you want to measure moment, if you want to measure drag force, if you want to measure anything. If you want to look at where, where a certain phenomenon occurs, you can look at that on your model system and it's going to directly translate to your real system. Super powerful experimental technique, but that only occurs if you can match like all of these different things. So we'll look a little bit at this bus and see how that works in real life. We're looking at aerodynamic drag on the bus. So we can either from having done experiments like this, or we could go back and look at the Buckingham pi theorem. We went through this to kind of develop what actually are the key parameters, the things that we need to look at. We want to look at drag force and velocity and size and viscosity and density and all of these things, but we don't actually care about them independent of each other. We care about very specific groups of those things. So we really only care about two groups of things. We care about that top one, which is our independent or our dependent parameter, the drag. It's a non-dimensional drag, but that's the drag force. And the bottom one, which is our like fluid flow characterizing thing. So what we have really is the drag coefficient, which is that top one. And we have the Reynolds number, which is obviously 1 over that bottom one. So the key insight that we can make through arguments of what we call similarity is that if we have like the same shape and the same basic flow, if we match Reynolds numbers, then we match drag coefficients. Just to see kind of how that would look visually. Right, this was the drag on a sphere. If you remember, right? So this is experimental data from a couple different experiments. Come on. So essentially what we're saying, apparently my pointer isn't working. Essentially what we're saying is if we're at the same place on the x-axis, then we must be at the same place on the y-axis. We don't know beforehand what the shape is of this curve. It could kind of be anything. Could be anything, but we don't know what that is. But we do know if we find ourselves at the same spot on the x, we find ourselves at the same spot on the y. And that's kind of the insight that we're looking at, is let's match our position on the x-axis, and then we know we must have matched our position on the y-axis. So let's look at how that happens for our bus. Okay. So for our bus, we have these two different systems. We have a real bus and we have a model bus. So we know a couple things about our real bus. We know how big it is. We know how big we're going to make it. Maybe we haven't actually made it yet. We know it's 8 feet wide. We also know what the cross-section area of the front is going to be. So it's an 84 square foot frontal area. And we care about this bus traveling at highway speeds. So let's say we care about the drag force at 100 kilometers per hour, like 60 miles per hour. We care about what's the drag force at highway speeds. We're going to be trying to investigate what's happening on this real bus with our model system. So our model bus is 1/16 scale. So then our width is 1/16 times 8 feet. So it's a 1/2 foot wide, 6 inches wide. Give a sense of how big our model actually is. And the area is 1/16 times 1/16 times 84 square feet. So this is 0.328 square feet. Okay, we'll switch units from feet to meters because that will make our lives a little bit easier. So the width of our model is 0.152 meters. And the area is 0.0305 meters squared. Okay. So we have these two different systems, our real bus, our model bus. We took a whole bunch of data, right? We took all of this data here in our wind tunnel on our model bus. We want to see how does that inform the actual real size bus. So we want to look at these two parameters, drag force and Reynolds number. So we have our drag coefficient, which is drag force over 1/2 rho v squared A. This drag force, we measured that. We have experimental data for the drag force. Right? We put a little force sensor in, we measured the drag, we measured the force on our model. We measured the wind speed. So we measured V. This is our model size, or our model cross-section area, or our real bus cross-sectional area. So we know that from the size of the object. And we know the density of air is 1.23 kilograms per meter cubed. At 1 atmosphere. So we actually know all of the different pieces for our drag coefficient. So we'll be able to calculate that. The other thing that we care about is Reynolds number, which is rho v w over mu, or v w over the kinematic viscosity. So again, that's the kinematic viscosity is a property of the gas. So nu is 1.46 times 10 to the minus 5 meters squared per second for air at 1 atmosphere. Okay. The velocity, then we have data, and the width, that's from our model. size. We know how big the model is. So what we're going to do is try to match. We'll be able to calculate Reynolds number and drag coefficient from our data. Then if we match Reynolds numbers, we match drag coefficients. So we have kind of a target for our real system, right? This is kind of our target. The Reynolds is equal to velocity, width over kinematic viscosity, which is 100 kilometers per hour, 8 feet wide, divided by 1.46 times 10 to the minus 5 meters squared per second. So we obviously have to do some massaging of the units. So 100 kilometers per hour, there are 1,000 kilometers in a meter, 3,600 seconds in an hour. So that's 27.8 meters per second. And 8 feet is 2.438 meters. .46 meters squared per second. So the Reynolds, we'll write it this way, the Reynolds for the real bus is 4.6 times 10 to the 6. Okay. That's our target. We want to get to that Reynolds number in our model system, and then we can say the drag coefficients are going to be exactly a match and we're all happy. Our experiment worked. Our experiment directly was modeling what's happening in the real system, and we can directly make the connection. So let's see if we can do that. Okay. Did I lose you? My back? Can you see Excel? Yep. Can see it? Okay. So we're going to take, got to look again at where my, oh, come on. I lost my data. Nope. Come on. And have two things up at once. There we go. Okay, there's the original data. Okay, so I have my the data that I took from the model. We have the airspeed, meters per second, and the F drag in newtons. Okay, our airspeed was 18 meters per second, 21.8, 26, 30.1, 35, 38.5, 40.9, 44.1, 46.7. Those were our airspeeds. Our drag force, 3.1 newtons, 4.41, 6.09. Okay. 18.9. All right, cool. So there's our model data. We can then calculate Reynolds number and the drag coefficient. So the Reynolds number is velocity times our width, which in this case is the model's width. So 0.152 meters divided by was what, 1.46 times 10 to the minus 5. Okay, and then we can just drag that down and calculate it for all of those. I'm going to make it look a little bit happier. And then we'll calculate drag coefficient, which is equal to force divided by 1/2, 0.5 times density times velocity squared times our area, which was 0.0305. We'll make it look a little bit happier. Okay, so now all we have to do is match the Reynolds numbers here in this left column, and then that will tell us exactly what the drag coefficient is in the right-hand column. Anybody see any problems? What's the problem? It's not on there. It's not big enough. So this is a cautionary tale in how it can sometimes be challenging to make models that actually work. And by work, I mean like that actually like fully represent real systems. So let's think to how we would go about designing that. Okay, so we want a Reynolds number of 4.6 times 10 to the 6. What we got was a Reynolds number about 1/10 as big. So why don't we just do an experiment like keep making the Reynolds number go up? Okay, so there are a couple ways to do that. We have like kind of 3 knobs that we can turn. One is the model size. So if we make the model bigger, why don't we make the model 10 times as big? That would work, but it kind of ruins the whole point. Instead of a model that's 1/2 foot wide, now all of a sudden we have a scale model that's 5 feet wide. We could do it. It's still going to be better than an 8 foot wide full-size bus, but like, why don't you just go the full distance then at that point? Okay, so what else can we do? Well, we can keep going up in airspeed, right? Velocity is on the top of the Reynolds number, so let's just keep going to faster and faster speeds. So we have to go up like a factor of 10 in speed. We're at 46 meters per second. So we'd have to go up to 460 meters per second, which is over the speed of sound. So that's not a super encouraging path forward. So what's the other way that we could do it? Well, we could change either density or viscosity. Right? Those both show up in the Reynolds number. So how would we change density? We could go to different pressures. We could change density by a factor of 10 by going from 1 atmosphere up to 10 atmospheres. But then we would have to be doing a wind tunnel experiment with a pressurized wind tunnel. You could do it, but again, you lose some of the advantage of like a quick and easy experiment. So you can sometimes run into roadblocks like this, trying to design the perfect experiment that takes all of the conditions from your real system and like perfectly matches it. But it doesn't necessarily mean that your experiment was in vain and that all is lost. So let's look at this data. I'm going to plot it up right now. Okay, so if we just make a quick plot, what you'll see from this chart is, okay, the Reynolds number on the bottom, the drag coefficient on the left. I'm not going to spend my time formatting it, but you can see, obviously, as you go to a higher Reynolds number, the drag coefficient goes down. But then once we get to about here, 3 times 10 to the 5, we're pretty flat, right? Like all through here, it's pretty flat. Again, more or less. So we need to go up again, like a factor of 10. But in this region, we're fairly flat. So occasionally with experience, again, let's look at what happened with a sphere. This is the drag force on a sphere. We see somewhat similar things happen. We see this region of lower Reynolds number where we're seeing the drag coefficient changing a lot as we change speed. But then we kind of like settle into this happy spot right here where we change speed. We change Reynolds number by a factor of about 1,000 from 10 to the 3 all the way up to 10 to the 5. And the drag coefficient is flat through that entire range. Okay, and then we go above 2 times 10 to the 5, and all of a sudden it like falls off a cliff and is totally different. So occasionally, and it turns out this happens to be the case for this bus that we're looking at right now, occasionally you can take kind of your intuition because you have experience running these things, you've done it a lot. Like, you know, okay, when I hit that flat part, I'm in this kind of a region here, and my drag coefficient is going to be flat for another, you know, factor of 10, factor of 100, factor of 1,000 maybe in Reynolds number. So I can like extrapolate out and be okay. So it turns out that you can actually do that reasonably well for this specific problem. So I'm going to, we'll flip back to this. To our notes, to say, like, sometimes getting true what we call dynamic similarity is sometimes really, really difficult. It's really difficult to design the experiment, or maybe it's cost prohibitive to design the experiment. Like, we could do it. If we ran this experiment at 10 atmospheres and redid all of our data, it would work. Yeah, Ryan?
What about changing like viscosity though? So like corn syrup.
So yeah, so the question is, what about changing viscosity? So you have to have viscosity. Viscosity is in the bottom of Reynolds number. So you have to have viscosity go down. So for viscosity to go down below that of air is challenging. So to really get like a factor of 10 decrease in viscosity, it's not super straightforward. So you can change it a little bit with temperature. You can change it a little bit with some stuff, but temperature changes density again, so those kind of offset each other. So it's not super straightforward to be able to do that. And you run into this in a number of different types of problems where the experiment that you want to do, for whatever reason, it's really hard to actually design. So we didn't achieve dynamic similarity. So we found that like the Reynolds number for our model was less than about 4.6 times 10 to the 5. So we never got to a high enough Reynolds number. We did, though, get close. So we did achieve, I'll write it with a capital G, geometric similarity, right? We had a good model, and kinematic similarity. right? Our model was good. The kind of the general picture of the flow was good. We just didn't quite get the right Reynolds number. We can sometimes extrapolate if we have experience. I'm going to give that a big underline. So this is where I wanted to show you something like this to show like this, the whole argument of similarity is that you can get kind of these fundamental properties to match, and then you can design experiments that actually capture what's happening in real life. And that's true, but sometimes the experiments themselves are really hard to make, and you can only get like part of the way there. But that doesn't mean like all is lost and you didn't gain any information about what's happening in the real life thing. Sometimes if you have a lot of experience with systems, you can extrapolate out and say, well, maybe, you know, if we expect the drag coefficient to stay about constant for the next order of magnitude. So we can estimate, in this case, we estimate C drag is about constant with Reynolds greater than 3 times 10 to the 5. So at a Reynolds of 4.6 times 10 to the 6, which is where our real system was, CD is about equal to 0.46. Okay, but this, to do that, to make that jump, takes experience with these systems. And this is why I know that at least most of you have seen this. If you were to say work in the automotive industry doing testing on a bus, you would do scale model tests like this. But you've also seen like wind tunnel tests on car commercials and stuff where they look at wind tunnel tests on full-size cars. They have to do those. They do it on full-size cars because eventually you have to scale it up, and you couldn't get all of the information that you needed from a small scale model because you couldn't get the Reynolds numbers to match. So the easiest way to go about it is not to do something too, you know, outside the box, like to do high pressure wind tunnels or something like that. It's to let's scale up our model and do it on a full-size prototype. And that's really the way that you have to, you can make extrapolations and estimates, but to get all of the information that you need, like we got to do the experiment with the full-size thing. So sometimes models can get us all the way there in the best cases. Sometimes they get us part of the way there. Even in cases where they get us part of the way there, they can provide a lot of valuable information, like over and above what you could get with a computational experiment. So we still often will do them, but sometimes you need to do, right, like a mix of small scale models and full size model and computation, and do like all of these things to start to get at how real systems are going to perform. That's something that really you can only make that leap with real world experience. And that's where kind of your intuition, working on problems and working on projects and what's going to actually happen if we do this, that's where that's kind of invaluable. To be able to make these kind of leaps that we expect the drag coefficient to be about constant. Maybe it is, in this case it is, but right, unless you have experience, you don't know if you're at this part of the curve where things are constant, or if you're at this part of the curve where all of a sudden things fall off a cliff. So you really have to be careful with with some of these things, there's a lot to be gained from experiments like this, but it's not a silver bullet that you can do and completely match the conditions for any full-size model system that you might want. Sometimes to get to those conditions is just hard. If you can, it's great. Sometimes it's really difficult to actually do. Okay, but if we can make this leap in this case, just to show you, we can then take this data, right? If we now have an estimate of the drag coefficient, we can say for our real bus, we expect drag coefficient to be about 0.46, which equals F drag over 1/2 rho V squared A, which is equal to F drag over 1/2. Rho is 1.23 kilograms per meter cubed. Velocity was 27.8 meters per second, that's squared. And area, about 7.56 meters squared. Okay, so we can plug that in. So for our real bus moving at highway speeds, we expect the drag coefficient or the drag force, not the drag coefficient, to be about 650 newtons at 100 kilometers per hour. Right, so this is again for our full-size bus. If our data had been better, if we could have done a better experiment, then maybe we could have matched our conditions better, and then been more confident about this number. So as it is, this is a good estimate, but it's something that we can only make kind of given an experience with similar types of systems. So this the idea of similarity, it's how we design a lot of experiments in engineering. How you choose the conditions for your experiments and try to match scale models to full-size models. But it's challenging in a lot of cases to make things match, have things match perfectly. Another common example, so like objects in cars and buses and those kind of things, aerodynamics is one example where we commonly run into this. Another example where you really always run into this is drag force on large ships. You kind of choose and pick and choose. We can only like partially match the conditions. So you have to have a lot of experience with how do we design good models of some of these kinds of objects. And we still try to use some of the same kind of guiding principles for how you design those model systems, but in practice, it's not always clean cut. Okay. So to end today, because we have a couple minutes left, we're going to watch a video. And the video that we'll watch, this is going to kind of introduce what we're going to start talking about really next week, Wednesday and Friday, which is to get a little bit more concrete understanding around aerodynamics and surface roughness and boundary layers and some stuff that we've been talking a little bit about here and there. So this one, as we have a couple of minutes left, this is a kind of a fun video that I think does a nice job of introducing some of these topics, but in an interesting way. Also know we have a lot of soccer players in fluids. So we're going to watch a soccer video. Okay. So let me get all my sharing stuff right. So we'll stop that. We'll start. Okay, can everybody see the? Okay, you guys can see that? Cool.
That's what a typical soccer ball, right? It's as simple as black and white. But that's not exactly what World Cup balls have always looked like. So what's the deal? First things first. You want a soccer ball to be as spherical as possible. In the old days, we had balls that had the buckyball shape, you had a center shape, you had the 20 hexagons, 12 pentagons, and that was a very good approximation to a sphere. It started in 2006 in Germany with the ENGS ball. There were more creative ways to make an approximation to a sphere. New technology enabled Adidas to start designing the balls with fewer panels, which actually created a serious problem because fewer panels means less seams. And more importantly, a smoother surface. The ball gets too smooth, the air resistance for certain speeds goes up. It's like picking a beach ball. And that's exactly what happened in the 2006 Team Geist ball. Players complained that the ball didn't go where they expected it to. So in 2010, Adidas compensated by adding some texture to roughen up the surface. Problem solved, right? Jawline was a spectacular failure because it was not rough enough. When the ball was kicked at certain speeds, you'd notice it looked like it would slow down dramatically in the middle of its flight. And the panels kept disappearing. The 2014 ball had the fewest panels yet, 6. This time, Adidas compensated. Despite having 2 fewer panels from Jawline, the total seam length around the ball was actually 68% longer than it was for the Jawline. So at least this time, the ball had the right amount of roughness and flew further than the 2010 ball. As for 2018, total seam length is small. It's actually 30% longer. So now you're at the risk of the ball being a little too rough. Again, Adidas compensated for this by also making the seams shallower. And studies show that Telstar 18 performs similarly to the Brazuca, but still has a bit more drag and might not travel as far in high-speed kicks. Regardless, all this begs the question. The goal is to produce a ball that's similar to what athletes practice with for years. Why does the world keep changing? Turns out it's not about the players or the game at all. I'm sure you can guess what it's all about. There's a new ball released for every World Cup, and I think the primary reason is money. The 2018 World Cup ball costs more than $100. And these balls fly off the shelves. It's a pretty big investment, considering you can get a simple replica for $20. Though they're not exactly the same. The technologies involved in these balls are much greater than the ball. The panel of these balls are perfectly bonded, helps keep the water out of the inside of the ball, the water, making the ball a water ball heavier. But is it worth it? We'll let you figure it out.
All right, so we'll talk next after our exam a little bit more about why in the world that does what it does. I hope you guys have a good weekend, have a chance for a break as well as studying and stuff as we wrap up the semester. Have a good weekend, guys.